Welcome to the second week of the online course on matrix method of structural analysis. What we have done in the last week is we briefly reviewed some of the concepts of equilibrium equation, then the compatibility conditions. We talk about what is stiffness, what is flexibility. We also talk about static determinate structure and statical indeterminate structure, kinematic indeterminacy. And then what we do today is, or this week is, we'll review the some of the methods for solving indeterminate structures. There are two class of methods. One is force method and what is displacement method. We'll see what are the, we'll review rather what is the concept of force method, displacement method, what are the different kinds of force method and displacement methods, and briefly review them. Okay. So, today is the sixth lecture and it is the statically indeterminate structure, review of statically indeterminate structure, force and displacement methods. Okay. If you recall what we have done so far, you see, suppose we have a structure, suppose we discuss that, suppose this force, when we say that force, it accounts for everything, force, moments, everything is a vector. Suppose it is a force and this is displacement, this is say displacement, okay. And again when we say displacement, it accounts for displacement, rotation, everything. And then these forces, these are static variable, this is static variable and this is kinematic variable, right? Kinematic variable. Okay. Now, what for given structure, we know that force and displacements, they are related through stiffness and flexibility matrices. For instance, if we can write say K, which is say stiffness matrix, and then displacement, this is force. We discussed that in the last class. Similar relation we can have that say another matrix, say F, we have used F. So, okay, say it is, let's take its, let's take it is, say instead of F you take say it is D, okay, D, and then F is equal to U. We have seen that where K is the stiffness matrix and D is the flexibility matrix. Okay. Now, when we, the main purpose of structural analysis is to find out either forces for a given displacement or either forces for a given displacement or displacement for a given force. Now, stiffness and flexibility, they are the properties of a structure. For a given structure, it depends on the material of the structure, it depends on the geometry of the structure. So, for a given structure, stiffness and or flexibility, which is the inverse of stiffness, they are known. Now, when that structure is subjected to certain amount of load, then we want to find out the displacement, or if the displacements are known or the kinematic variables are known, we need to find out what are the static variables. Now, depending on that, so when we, so either U can be, so the main purpose is to find out U, the kinematic variables for a given with the knowledge of static variable, or find out static variable F with the knowledge of kinematic variable U. So, how we frame the problem, whether we use this definition or this definition, both definition tells you the similar thing, but these definitions are different in the sense that your unknown are different. In this case, in the first definition, your unknown is U, kinematic variable, and in the second definition, your unknowns are force. So, which we take as our primary unknown, depending on that, we can frame the problem in a two different way. One is the force based method and one is displacement based method. As name suggests, force based method is the forces are the primary unknown, where we use this definition, where we use the flexibility matrix, and for a given kinematic condition, with the knowledge of kinematic condition, we determine the unknown forces. And for displacement based method, where the static conditions are known and we determine the kinematic condition, the kinematic variable using the stiffness relation. So, that is the main, that is how these force and displacement methods are different, but then since their definitions are different, we are using it, we are using different representation of the equation. Naturally, the steps will be different, there will be differences in the steps. Okay. So, let us try to understand, or rather try to review what are the different steps that we follow in force and displacement method. Okay. Force method, as I said, since it uses the flexibility definition, it is sometimes called flexibility method, and also displacement method, which uses stiffness definition, which is also known as the stiffness method. Okay. So, since in the force method, since your force is the primary unknown, so the number of unknown depends on the number of additional forces or additional constraint, additional reactions or additional internal forces that we need to find out. So, therefore, the number of unknowns depends on the what is the static indeterminacy of the structure NS. Now, on the other hand, if it is displacement method, then we need to find out displacement. Then the number of displacement need to be found out in order to define the configuration of a structure or the configuration of the deformation is the kinematic indeterminacy of the, that is called kinematic indeterminacy. The number of unknown in this case is kinematic indeterminacy. The force based method we need to find, first step would be to find out static indeterminacy, and the displacement method find out the kinematic indeterminacy. Then identify the redundant forces. Redundant forces means the forces that need to be computed. Okay, that need to be determined, which are to be considered as unknown. Now, in this case, again we need to identify the unknown displacement, and the number of unknown displacements are equal to the number of static kinematic indeterminacy. Now, then in the force method, the third step is find displacement in the basic statically determinate structure. We will just demonstrate this both the methods through one example. We need to, once we have identified the redundant forces, then we need to split the entire indeterminate structure into several statically determinate structure and then solve them. And then in this case, in the displacement method, what we have to do is we have to restrain the above displacement, the displacements which are unknown, and find the forces in the basic kinematically determinate structure. So, in this case we need to divide the problem into several sub problems, that is sub problems become statically determinate, and the displacement method we need to make the problems kinematically determinate. Okay. Now, the next is once we have divided the entire problem into basic determinate structure and calculated the internal forces and the displacement, then in the force based method displacements are expressed in terms of redundant using flexibility format that we just now discussed, and in this case it is the forces are represented or related through displacement using stiffness format. Now, once we have the representation, then the next step is the solving a system of linear equation. In the force based method, then we solve for the redundant forces, and in the displacement based method, we solve for the unknown displacements. And once we have solved for the unknown forces and unknown displacement, rest of the things become then straightforward. Rest of the thing is substituting those unknown forces, the additional forces which are unknown, into the static equilibrium equation and then solve them all. So, so you can recall the steps that you followed in force and displacement methods and try to find out the relation between the differences that just now we discussed. What we will do now is we will just before that. The force based method you might have studied in structural analysis 1, the method of consistent deformation is a force based method. Then you started in displacement in structural analysis 1, slope deflection method, moment distribution method, they are all displacement based method. Direct stiffness method, if you have not done in structural analysis 1, direct stiffness method, then it is also fine, because we are going to discuss the direct stiffness method in detail, which is essentially the basic concept of matrix method of structural analysis. Okay. So, what we do in this week is we just briefly review all these methods, the method of consistent deformation, then slope deflection, moment distribution, and then set the platform so that we can go further and formulate the basic purpose, the objective of this course, matrix method of structural analysis. Okay. We will start with today, we will start with force method, method of consistent deformation. So, we are going to, we will be discussing the steps followed in force method through one examples. Okay. Now, let us take one example. So, force based method, let us first define force based method. The force based method is essentially we take the redundant forces, the forces are unknown, and the additional equations are obtained when we say the statically indeterminate structure or any indeterminate structure. It means that there are some unknown for which we do not have equations, and we have to formulate those equations, and how those equations are formed, based on that we have different methods. Now, in this case the forces are unknown, and then the additional equations are formed based on the compatibility, okay, and then we solve them. Okay. So, let us take one example. This is a statically indeterminate structure. We need to find out what is the, we need to analyze the structure, means we need to find out the internal forces and displacements. Okay. So, as we know, since it is statically indeterminate structure, just equilibrium equation are not enough to completely analyze the structure, to find out all the unknowns. We can probably partially solve some of the unknowns can be determined through equilibrium equation, but not all for indeterminate structure. The first step is to find out the static indeterminacy. So, in this case the static indeterminacy is 1, this is a fixed support. So, we have 3 reactions here, if you recall the characteristic of supports, and then it is roller support, we have 1. So, here it is 3, it is 1. So, total number of unknown is 4, and then number of equations, equilibrium equations available is 3, summation of force is equal to 0, summation of Fx is equal to 0, summation of F force in y direction is equal to 0, and summation of moment at any point is equal to 0. So, total 3 equations. So, in this case static indeterminacy is 1. Okay. So, once we determine the static indeterminacy, next step is to selection of redundant forces. This is a very important step. You know, if again you recall that we need to make the structure, what is the purpose of selection of redundant force, because that is the force we are going to be unknown. Now, and then based on that force we have to decompose the entire structure into basic determinate structure. Okay. Now, redundant force should not be such that when we decompose the structure into basic determinate structure, your basic determinate structure become unstable. And based on that, I will give you what does it mean when I say that, when I make this statement through one example. Okay. So, in this case, you see, in this case there are 2 possibilities. We can choose redundant force. One is take the support reactions at support reaction here as redundant force. Means, you see, it is a propped cantilever beam. Had it been like this, and then we have a load like this. This is A, and this is C, and this is B. Then the structure is determined, it is a cantilever beam. Okay. So, this additional, this propped at point C is extra. So, the reactions at point C is additional reaction. So, therefore, we can assume, we can take the reaction at C, which is Cy, as the redundant force. So, this is the one case. Okay. Now, if we do that, if we take this as redundant force, so if we do that, this has redundant force, the next step is we have to, using based on this redundant force, we need to decompose the entire structure into basic indeterminate structure. Now, so this structure can be now decomposed into two parts using linear superposition. Okay, one is the cantilever beam, where there is no support at all, and then there is another cantilever beam where we have just the support reaction. So, together these two gives me, so these two gives me this, that is the superposition, right, linear superposition. As long as your force displacement relations are linear, we can have the linearity in the system, this superposition is applicable. Okay. So, this is case 1. Case 1 means this is the one way we can we can choose that Cy as redundant force. So, let us see is there any other possibilities. Okay. Another possibility would be say again in this structure, if we remove the if we remove this fixed support here and make it hinge, this becomes, it is hinge support and this is roller support. This structure is still this is P, this is A, B and then C. This structure is still determinate structure, okay, and not only that, it is stable structure. Okay. So, we have removed the moment constraint at A. So, in this case the moment at A, MA is taken as redundant force. So, either we can take support reaction at C as redundant force or moment at A as redundant force, that's you have to decide. Okay, once we take this as redundant force, then the basic determinate structure becomes this, where there is no reactions, no basic determinate structure become your simply supported beam in this case, but then in this case there is no restraint, no moment, and in this case it is only subjected to external load and then it is only subjected to the redundant force. Now, this is how we can take, there are many possibilities, you can check whether other reactions can be taken as redundant force without compromising with the stability of the structure. Now, just give you an example, consider a truss. I will go back to this problem once again. Just since the step 2 is very important, let us spend 1 or 2 more slides on step 2. Take another structure, another truss, which is again a indeterminate structure. If you can see here, the number of reactions are 2, here also number of reactions are 2. So, here it is 2, here it is 2. So, total number of reactions are 4, but as far as the number of reactions are concerned, we can have 3 equations. So, it is redundant forces 1, your static indeterminacy is 1. Okay. So, now one case 1 is we can take this as redundant force, we can take say this as redundant force. Now, we can take this as redundant force, means this was a redundant force. The vertical reaction means Cy as redundant force. If we take Cy as redundant force, basic indeterminate structure is 1. So, in this case Cy as is redundant force, there is no restraint at C in y direction. Now, another possibility is we can take Cx as redundant force, Cx as redundant force. So, there is no restraint, this is Cx as redundant force. So, there is no restraint in x direction. Okay. Now, let us see whether both the cases are valid or not. We can continue the analysis by taking any of the cases or not, or applicable or not. Now, let us see what happens in the case of in this case, means case 1. Okay. Case 1 is, this one is the case 1 where Cx is Cy is the redundant forces. Now, if it is subjected to, so Cx is the redundant force. Now, you see if it is subjected to some load P, then this may deform like this. This may this may collapse, the entire structure may collapse like this. So, what happens? So, this is not a stable structure. So, case 1 is we cannot continue our analysis with case 1, but see what happens in the case of case 2. Case 2, this is unstable structure. So, this cannot be taken. Take the example of case 2. In this case, your redundant is Cx is the redundant, right. Now, if we take Cx as the redundant and then apply, if it is subjected to some load P here, then it may be it may deform like this. So, in this case it is stable, and therefore, we can take Cx as redundant force. So, when you choose a redundant force, it is very important to have some understanding about the stability of the structure. And the stability of the structure, if you recall in your structural analysis 1, stability of the structure is something that we have to judge based on looking at the configuration of the structure. Yes, there are equations, there are we can see what is the indeterminacy of the structure, whether the positive or negative. Based on that, we can comment on the stability of the structure, but there are some examples where we can show that just your indeterminacy is static indeterminacy is negative, but the static indeterminacy is positive, the structure is indeterminate, but still the structure is not stable. The stability of the structure is something that we have to judge based on our engineering sense, okay, and that is a very good thing that we all must practice. Okay, so once this is done, again go back to our original problem, this problem. So, let us continue the analysis by taking Cx as the redundant, Cy as the redundant. Now, if we take Cy as the redundant, these are the basic indeterminate structure. Now, the next step in this case is to solve this basic indeterminate structure. Okay. Now, when we solve this, means we have to find out the displacement, moments and everything. And then first is this the basic indeterminate structure 1, where it is cantilever beam subjected to the external load, and if we solve it, then your displacement at this is the deflection profile, and this is the deflection at point C, and this deflection will be something this. So, that we know how to determine. We have learned it in structural analysis 1, right. Now, another basic indeterminate structure is the second one, which is cantilever beam subjected to the redundant force, and if your deflected shape will be like this, and the deflection at point C will be this. Deflection at point C will be this. Okay. Now, once we have determined the deflection for all the basic indeterminate structures, then the next step is to use the compatibility condition to have an additional equation. And now, let us see what is the compatibility condition. Compatibility condition, if you recall, it says that the deflection profile should be such that it should satisfy all the continuity requirement, differentiability requirement, and also the boundary conditions, all the constraints. Then only you can say the deflection is continuous or deflection is compatible. Now, you see, in this case, one condition we know for this structure is actually in the original structure was like this. Original structure was a cantilever beam, a propped cantilever beam, right, a propped cantilever beam. This point is C and this point is A, and then you have a load at B, point B. Now, one condition is for sure, irrespective what may be the deflection of the beam, what may be the forces, moments, but one condition with absolute certainty we can say that the deflection at the vertical deflection at point C has to be 0, because that is the support condition. Okay. So, we have given a constraint in vertical direction. So, C delta C has to be 0. Okay. Now, the superposition says, the linear superposition theorem says that the response of the entire structure is now can be obtained by response of their response of the individual sub problems. So, if we add them, then we get the response of the actual structure. So, response of this structure, response of this structure or the deflection or at point C should be equal to deflection obtained from this basic determinate structure plus the deflection obtained from this basic determinate structure, and that total deflection has to be 0. So, that is the additional equation that we have. Okay. Let us see then what is the compatibility condition. Compatibility condition says that delta CC, this should be C here, this should be CB here, this should be CB. So, this plus this has to be equal to 0, right. Now, if we make it 0, then what it becomes? It becomes CY is equal to this. CY is equal to this. So, your reaction at C is equal to this. So, now once we know the reaction at point C, the next step is this is now known. If we apply the free body diagram, this is the free body diagram. In this free body diagram, initially before doing all this exercise, initially we had 4 unknown Ax, Ay, 1, 2, 3 and then 4. We had 4 unknown, 3 equations, summation of fx, summation of fy, summation of fx is equal to 0, summation of fy is equal to 0, and let us say summation of moment at A is equal to 0. We have 3 unknown, 3 equations, 4 unknown cannot be obtained. But now, after doing all this exercise, this is Cy is no longer an unknown. So, Cy is known, Cy is now known. So, essentially we are left with 3 unknown Ax, Ay and Ma, and applying these 3 equations we can obtain these 3 unknown. Okay. Now, once we obtain this, then rest we can draw the bending moment and shear force diagram. So, Cy is equal to this, which is known, and with this known Cy we can obtain Ax, Ay, and draw the bending moment and shear force diagram. This is the bending moment and shear force diagram. Once you have the bending moment and shear force diagram, then you can determine the deflection slopes at any point using any method that you studied for statically determinate structure. Okay. So, this has been a very small demonstration or the review of force method or method of consistent deformation. Next class what we do is we will have a brief introduction to displacement method and then review some of the displacement methods, that the list that we gave, and then we see how this displacement method can be taken forward to form a very general method which is the topic of this course, matrix method of structural analysis. Okay, then see you next class. Thank you.